In Germany, Heather Cooper introduces a close encounter of the second kind.
Hello and welcome live to the European Space Operations Centre at Darmstadt in Germany. I'm in the centre of the main complex in reception, which was actually an awful lot busier here a few moments ago, as hundreds of guests from all over the world streamed in to witness with me one of the greatest space encounters of International Space Year 1992. The encounter between a comet and the probe which went to see Halley's Comet back in 1986, a close encounter of the second kind. This programme's coming to you in English, even though we're coming out of Germany, because that's the common language used here by the engineers and scientists who work here controlling the probe and looking for the comet. The engineers are in mission control over in that building over there. They're making sure the probe is targeted right into the heart of the comet, and the data goes to the scientists in there. Many scientists from many European member states who are getting together to bring you some very exciting news this afternoon. Well, as you can imagine, it's action now. It's really crowded in both mission control and the scientists' headquarters. So what we've done is to organise that this whole programme and all the data that comes and all the exciting scientific discoveries from Comet are coming to you in another room. And this room is packed with dignitaries, as I hinted, from all over the world, including heads from NASA and also from Russia. So it's a fully international jamboree going on here this afternoon. And of course, some young scientists whose careers actually started off with Halley's Comet back in 1986. And as I walk into the room, I can't help to tell you the thing that really zaps you in the face. Thank you. Thank you, everybody. The thing that really zaps you in the face is the full-scale mock-up over there of our space probe. That's our hero for today, by the way. It was built for especially by British Aerospace in Bristol in collaboration with Dornier in Germany. But our story starts at a conference in Padua in Italy in 1981 when they gave the space probe its name. They called it Giotto.
The name comes from a painting by the Italian Giotto di Bondone, who saw Halley's Comet in 1301. Compare that with the view from Earth in 1910. Seen from the ground, its return in 1986 was disappointing, but the Giotto mission to Halley's Comet produced spectacular discoveries. The spacecraft was damaged, but not destroyed. As it flew away from Halley, it was preserved in hibernation until a decision was taken on what to do with it next. 4 years later, as it came back towards Earth, it was reawakened and sent to its second target. First identified by New Zealander John Grigg in 1902, then a few orbits later from South Africa by Grigg-Skjellerup, their faint comet without a tail promises to be very different from Halley.
Today's target, Comet Grigg-Skjellerup, that's our second hero. Giotto will cross its orbit, as you can see, in about an hour's time, and it's still 56,338 ticking down kilometres out. And the Earth is in this picture too. It's the little dot you can see right in the centre of your screen, 214 million kilometres away from all the action. Well, we can bring the action to you here with the help of Professor Johannes Geiss, who is probably one of Europe's most distinguished scientists who succeeded in getting cometary research actually off the ground and out into space. Johannes, I needn't tell you, you've participated in more than 20 space missions, including the Apollo missions, and of course you were very active in the Halley mission that Giotto was on 6 years ago. Why are you so fascinated by comets?
Comets are interesting, particularly interesting because they contain pristine material. That is to say, material which was not altered since the origin of the solar system 4.5 billion years ago. And by going there and probing the cometary coma, we can measure the contents, the composition, what molecules, what the dust made of these comets, and that tells us a lot about the origin of the solar system, but also of the origin of our Earth.
And life itself, perhaps. But why do we want to go to a second comet, since we've done old Halley?
Well, you know, Halley is a very big comet, as we have seen in these wonderful pictures. And we expect that Grigg-Skjellerup is very small and also much less active. Now, that doesn't mean it's less interesting, because we like to compare a big and a small comet, because the physical process, the chemistry, is rather different.
Sure.
And therefore, we have to have this comparison to understand better what's going on inside and around comets.
Well, as we all know, a comet is really all show. The dust and gas that you refer to form an enormous head, the coma. In this case, it's 60,000 kilometers across. But it all comes from a dark, mysterious nucleus hidden deep inside.
The Grigg-Skjellerup nucleus could be anything from only a few hundred meters up to nearly 2 kilometers across. But compared to Halley's nucleus, it must be very small. For that, in 1986, the scientists had 10 instruments aboard Giotto. The multicolour camera produced an image, but in contour maps of false colours, difficult for laymen to understand. But now they've been converted into a sequence of astonishing beauty.
Those pictures were beamed back to Earth from Giotto's high-gain antenna. Until something dramatic happened.
Transmission back to Earth was lost. The pictures disappeared. To viewers watching this on television, that looked like failure. And even the controllers were shaken.
Giotto, travelling at 50 times the speed of a bullet, had hit something the size of a dried pea. At that speed, it was like being hit by a hand grenade. Now, the bad news is that it smashed into the camera that took those pictures. And that means on today's encounter, there will be no new pictures. Giotto is blind. But it's far from helpless. Although it's handicapped, the battered, limping probe can sense its environment very well. In fact, after the bash with the particle from Halley, Giotto was back in business after just 20 seconds, collecting data with 8 out of 10 of its other instruments. And after 6 years, those instruments are now on their way to Grigg-Skjellerup. Now, you've said that Grigg-Skjellerup's a much less active comet than Halley, so surely there's no risk this time.
I wouldn't say that. There is, in fact, much less dust as we anticipated. The dust is also slower, so this makes for more safety. But, however, Giotto has a different approach this time, in a way. Instead of going with these dust shields into the forward direction, into the cometary dust, it has to go sideways to keep the transmission to the Earth. And therefore, most of the dust will hit these sides, hit the instruments, and in particular, the solar cells.
So they could be degraded?
They could be degraded.
Well, let's go over to where they're watching over the health and safety of Giotto in the control room. And we should have with us Manfred Grenzmann. In fact, at the moment, the spacecraft operations manager is Antonello Morani, but he's concentrating very hard on what happens to the spacecraft. So I'll talk to Manfred, because Manfred's been the project manager for the last 3 years. Manfred, why send a damaged space probe into a comet?
Well, the spacecraft was not so much damaged as we had expected when it would pass Comet Halley. It survived remarkably well, and when we did the first check after the Halley encounter, we found that several experiments were still working. Of course, the time was at that time too short to make a detailed assessment. So in 1990, we reactivated the spacecraft, and then we checked the spacecraft and the experiments out in detail and found that we could fly with the payload and with the spacecraft a second mission.
Fine. Well, as the flight operations manager who control, this is Howard Nye, who I can see sitting next to you. Hello, Howard. You look very busy. But how far away is the comet, and is this going to prove difficult for distances?
Well, the spacecraft is 214 million kilometers away from us at the moment. And this means that if we send messages to the spacecraft, it takes 12 minutes to get there and 12 minutes to get back.
Well, what if something actually happened? You'd lose your data.
Well, we have a series of contingency plans already here,
Yes.
and depending on what we see, if anything goes wrong, then we go straight into semi-automatic mode to take over contingency actions.
So essentially it's on its own. There's no way the control centre can reach it within 24 minutes. In fact, at the moment, talking of the timings, we have a time to closest approach at the moment of 1 minute 1:08. Is that time at the comet or is that time here?
That's the time on the ground. Of course, the encounter occurs 12 minutes before that in space, but we don't see it until the data gets to us on the ground.
So that's the Earth time. Well, let's stick with the Earth time because that's when the signal reaches us. That's what it's all about. Thank you, Howard, and I will be coming back to you later, often, little and often, we hope. Thank you very much. Well, whatever data comes back from the control center where they're flying the space probe, as you know so very well, Johannes, goes to the scientists. Let's take a look at the video bank and see what the scientists are up to at the moment. Have you had any news?
Yes, it's very good to tell that, of course, as we are approaching the comet, some experiments have definitely detected cometary material.
Yeah.
That is water which has been disintegrating. So we are sensing the comet.
Well, let's go and sense the comet over here. As you can see, just next to the model of Giotto, we have something which I think to some of you in the room who are not scientists will look like a kind of glorified cosmic jellyfish, but I assure you it's not. And I'm going to get Johannes to explain really what this model is meant to be showing you. This is our own Grigg-Skjellerup for the afternoon.
Well, inside here is the nucleus, a solid body emitting gas and dust because it's heated by the sun. And this gas expands, and then it's driven by the solar wind, which is coming this way in this picture.
That's a bit like the sun's hot breath, if you like.
That's right, yes. And formed into the tail. That's like if you have a chimney, smoke coming out, and the wind just carried it away.
And just here, where you have this, if you like, the comet's surface between the solar wind and the comet's gas, that's the bow shock, isn't it?
That's the bow shock. But we are, of course, outside it, but still there's cometary gases coming outside, and we sense it, and several instruments have seen it already.
So they're leaking out right outside the comet.
Right.
Well, let's go back to the video wall, because I can actually see one of our colleagues on the screen at the moment. That looks like Fritz Neubauer over there. And I might just ask him, Fritz, are you hearing me?
Yes,
You
I
are
do.
jolly good. I'll hand you over to Johannes in a moment, but your experiment essentially senses the environment of the comet. Anything you're picking up?
Well, we have the first indication of some weak waves, but they seem to be clearly of cometary origin. In fact, that's about half an hour earlier than we expected this.
What does that mean for you?
Well, one thing is, or one reason probably is that the solar wind is relatively quiet, so the background where we have to distinguish against is very low, so the situation for the detection of these waves is reasonably good.
What wavelengths do you have?
Well, the wavelengths are, I would estimate, a few thousand kilometers.
Goodness me. So if you could hear them, it would be a very low note. Johannes, I understand that Alan Johnston is wanting to talk to you over there at the moment.
Good, yes.
So while we get to him, it looks very... You see what I mean about it being crowded in there? It really is. And Alan's in the corner over there. Alan is in charge of the Johnson plasma analyzer. He has his own experiment named after him. And I think he can pick you up now, Johannes.
Yes, Alan, can you show us some pictures how you really see the cometary ions?
Yes, we're showing them now on your monitor. We first detected the pickup ions from the comet about 5 hours ago when it was still 300,000 kilometers from the nucleus. And since then, the density of the ions has been steadily increasing, and we're now getting some very interesting distributions, which you can see here on the screen, which are very typical of the cometary ion distributions that we expect. So it's behaving just as we anticipated the distributions would, and I think the density is building up nicely so that we're going to get some very dynamic effects before very long.
That's very exciting. Shall we go on to talk to somebody else, just so we don't disturb Alan too much at the moment? We have Susan McKenna-Lawler in the corner. Many of you who saw the previous Encounter programme might remember Susan as the lady in the red hat. Now I see she has changed into a very attractive purple outfit and having her headpiece put on at the moment so she can hear me. Susan, are you hearing me loud and clear?
Indeed I am. Hello, Heather.
Hello, Susan. Let me just first of all ask you about the name of your experiment, EPONA. What does it mean?
Well, it's an acronym for what the experiment does. It stands for Energetic Particle Onset Monitor, but it's also the name of a Celtic goddess who's associated with the commencement of the solar year. And if you turn your camera up above our place, you will see the Celtic goddess riding out to bring data back from the comet.
Well, good luck, Susan. That sounds very auspicious indeed. Again, we'll be talking to all these people later on. Now, some of those images might have been rather sort of difficult to follow to begin with, but in fact we do have one that's rather easier to follow. And this should be coming up on your monitor screen any moment. Yes, yes, it's coming, I gather. It actually will show you when you get it. We haven't got it yet, but never mind. The graphic we would have showed you shows how far in Giotto has got. But that's another question. Where's it going, and how close to that little lump we call the nucleus is it going? Now, for the best estimate to find out these details, what we need to do is to go to another department in the control building. We need to go to flight dynamics, and I'm relieved and delighted to see that Trevor Morley is there waiting for us at the moment.
Yes, hello
Trevor
there.
Morley, hello there. Are you actually aiming Giotto?
We are aiming Giotto directly for the nucleus.
Oh, you brave man. You're not trying to skirt it by 100 kilometres or so, as you did in the case of Halley's Comet. So what are your chances of hitting it?
Very, very, very small. 1 in several tens of thousands.
It was 1 in 40,000 the other day. It sounds to have shrunk just a little bit.
It's very difficult to estimate the chances, but we are confident we are going to fly by within a few hundred kilometres.
And what do you estimate your time to closest approach? How accurately targeted is that?
We estimate, we're relatively sure it will be between 17:30 and 17:31 local time this afternoon.
Right, we're all waiting for that moment of anticipation. Johannes, you have a point?
No?
You haven't got a point. OK. Well, let me ask you, Johannes, thank you very much, Trevor, indeed. You can get back to work now.
Thank you.
Johannes, how will we know when we're at the closest approach to the comet?
Yeah, that's a difficult question. If we had a camera, it's very easy. We know the speed, we fly by. If the comet seems to go fast, then we are close. If it seems to go slow, then we are far away. And you can calculate exactly the distance that we did in the case of Halley.
But you had a camera?
Yes. Now, this time it's a little more difficult, but in principle the same thing you can do. Take, for instance, the dust experiment.
Yes.
If we go very close by, the dust counts will peak very high, but also very shortly and come down very fast again, or the electron densities of Henri. So by looking at these other data, we can pretty well tell how far we were, and I hope even this afternoon we can already make our first guesses.
So you reckon that the dust experiment, the impact experiment, is going to be the one to tell us exactly how close we got?
Yes, we need the others, but that is most directly.
So let's take a look at this dust experiment. Using data direct from the spacecraft, this will tell us, as it happens, when dust begins to hit Giotto at 14 kilometres per second. Now, this is just a demonstration of what we're hoping for. That's it. Clunk, clunk. Microphones on board. This is what's really happening now. Not a lot. Hang on. No, not a lot. It's gone awfully quiet. So that's what's happening now. So there's nothing much happening. So I'll turn now to Tony McDonnell, who leads the dust impact detector team. And Tony, I can see you in vision now. When do you expect to run into dust?
Well, we don't really expect activity until about 10 minutes before encounter.
I understand that you've been betting on it as well. You're a sweepstake there, haven't you?
Well, we have got a sweepstake, yes, indeed. But the winner of the sweepstake has to buy champagne for everybody else. So I don't think there's a winner.
Incidentally, how do you measure this dust?
Well, the dust is measured by the piezoelectric detectors we have on that dust shield. We measure the impulse to the shield and can work out from that then the mass of the particle hitting the shield.
And how does that tell you how close you actually get?
Well, for each impact, on this trajectory here, we'll see a red light appear when we get an impact, perhaps about 10 minutes before encounter. So that from the distribution along this trajectory, then we'll be able to work out the missed distance. But we don't want this to start too early, or else it's bad news for the spacecraft.
It absolutely is. I hope you don't get too much dust, Tony. No. But anyway, I will say that from now on, we will be watching out for dust, just in case any gets further out than you're expecting. And we'll come back to you after closest approach to see what you can tell us then, and the sweepstake, of course. And there could be other clues from the dust, as there was at Halley's Comet. There, it was even possible to calculate how much dust Giotto ran into. How much was it, Johannes?
Just the amount of dust we see here was the total Giotto collected when it passed by Halley.
That's incredible. That's about getting on for maybe a couple of grams of dust?
Yes, something like that.
And that caused so much damage to Giotto when it went into Halley?
Yes, of course, you know, the velocity is tremendously high,
yes.
68 kilometers per second at that time. And, for instance, the largest particle we estimate was about this size. And the energy it ran into Giotto is comparable to the energy of a medium-sized car running on a highway.
Sure. So let's get away from disasters, because there were a lot of other discoveries too, from a range of instruments on board Giotto that flew into Halley's Comet to find out what it was like. One theory, triumphantly proved, was that all of this stuff we've been talking about came from a kind of dirty snowball, but scientists had no idea what it would look like. In fact, it turned out to be very dirty indeed. Much of the surface was black, but with icy craters from which gases and dust lift off towards the sun. They could also see what size it is. And how big was that, Johannes?
Well, Halley is 15 kilometers long and about 7 or 8 kilometers wide.
Mm-hmm. It doesn't sound very big to me.
That's right, but it's, of course, among the comets, probably one of the bigger ones. Certainly Grigg-Skjellerup will be smaller.
How do comets like Grigg-Skjellerup and Giotto hold themselves together?
This is not stickiness, this is really gravitation, like on Earth.
Yes.
And if you would stand on Halley's Comet, you don't just fall off. You really have to jump, you know.
Demonstrate.
Something like this. You really have to jump like this. And you just leave, you know.
Wonderful.
And I know you gave it a try.
I'm
earlier.
afraid I've got to confess, when we were talking about this earlier yesterday, I sneaked off into a studio and I'm about to demonstrate what goes on. I'm going to show you what it shows like if you actually go to Grigg-Skjellerup, and while we were talking about this is what it actually looked like.
I'm glad you're still here.
Oh, delighted to be back. I had a great time in space. Now let's see where we're getting on the video wall. At the moment, it's quite a long way. It's still 49 minutes 30 seconds to closest approach, and it's 41.5 kilometers to go. It means it's a heck of a long way from Earth, and you might well sort of ask, well, if it is such a long way from Earth, what relevance do comets actually have to us here on the ground? I thought what I would do is to put that question to some of the scientists who were here earlier yesterday. So why are you lot so interested in comets?
You see, from the Giotto encounter with Comet Halley, we learned that comets really are the most primitive bodies in our solar system. Comets have been stored since the origin of the solar system at the outer rim of the solar system in cold storage. They are very small bodies and they have hardly changed during this 4.6 billion years when the solar system was formed. And we believe that the comets, so to say, are the clue and bringing us the message from the distant galaxy. That means they, so to say, our door to the universe.
One of the great surprises of the Halley flybys was the discovery in the cometary dust of what we have called organic molecules. That means molecules with atoms that are known to be able to build up life. Of course, there was no life in Comet Halley, but we know for sure now that cometary dust is typical of interstellar dust, and in this dust there are huge molecules, and those molecules have been hitting planet Earth at the maybe 4 billion years ago, together with cometary water. This cometary water is very interesting. There is heavy water in it, with the same kind of ratio that in the Earth's oceans. Mm-hmm. So at the very beginning of planet Earth, 4 billion years, maybe 4 billion years and a half ago, on our tiny planet Earth, there was already the building blocks for life. And this miracle of life occurred at that time, maybe because of comets.
Is there anything we can tune into, Chantal, where solar systems maybe, stars are being born now?
Well, indeed, there are some regions, like Orion region, where we see today some stars that are born. There are huge clouds of dust and of gas that collapse for some obscure reason. And out of those clouds of dust and gas, some new solar systems are born.
Do we know any more about how solar systems actually are born? What happens after one of Chantal's gas and dust cloud collapses, Johannes, and how are the sun and planets born out of it?
This happened in our case 4.5 billion years ago, but we have very much indirect evidence. This cloud collapses and then it forms a disk. And in this disk, material begins to collect the Earth. Jupiter was formed, and in some places it also collects only into small bodies, and these are the comets, or the smaller planets. Now, the comets then were perturbed by the big planets like Jupiter or Saturn. Many of them just left the solar system. Others, a few, came to Earth, provided us here with water and carbon compounds, organic material, and many of them were stored very far away at the outer rim of the solar system, which we call the Oort cloud. And these are the comets which we now and then come to the inner part of the solar system, and Halley is one of them, and now Grigg-Skjellerup is one of them. So they are late arrivals.
Could they actually hit the Earth?
Comets could actually hit the Earth, but when they are perturbed from the outer rim of the solar system, that usually happens when a star passes by. But the passage of a star is still at a very, very far distance, so it's not a close passage. Then you have a very small gravitational disturbance, and that brings then a comet into the inner solar system. And so you have comets that just come in once in the inner solar system, then they leave it again. Or we have these periodic comets like Grigg-Skjellerup or like Comet Halley. They get another perturbation from one of the big planets. Usually it's Jupiter that really captures them to the inner solar system, where they stay like Grigg-Skjellerup, or they are on a very elongated orbit like Comet Halley, who only comes close to the Sun every 75 years.
I can't resist asking you the question, how big would a comet have to be to wipe out life on Earth?
If cometary nuclei larger than, is it 500 meters, is it 1 kilometer in that range, happen to hit planet Earth? A time life, it's something that can only happen very, not often at all.
Thank goodness for that. And people who've been watching close will realise I still can't read the time. I ought to learn how to read a clock. It is not actually 1 minute to go. It's actually 44 minutes to go. I forgot the hour. We've had some exciting news from Alan Johnson. I want to go right over to him now. Johannes, will you talk to Alan Johnson, who's waiting for us?
Alan, I understand you see the cometary ions, and could you perhaps show you a little bit more detail what you are seeing?
Yes, we've just noticed in the last few minutes that the cometary ion density has started to build up much more quickly than we had anticipated earlier.
Oh.
So if you look at the screen here, you can see that the line now, the blue line of the measurements, is running well above our line of predictions based on the earlier measurements.
So it's almost like Halley, huh?
Yes, in fact, what we're finding now is that the ion density that we're measuring at the moment is almost the same as the ion density outside the bow shock of Halley. So we could well be into a bow shock before very long. At the same time, we can see that the solar wind speed has decreased significantly, so the ions are slowing down the solar wind just as we had expected, but rather faster than we had expected.
So we are really getting in the middle of it, huh?
We sound as if we are. That's very exciting news. Can we come back to you later on that, Alan? That's very good indeed.
Yes, certainly.
In 1910, Halley's comet, which we just heard about, actually scared some people. It came close enough for its tail to brush across the Earth. In 1986, it was a lot farther away, but Giotto passed through its head, which is, of course, the coma of the comet. We've now heard enough about comets to look at the astonishing pictures Giotto sent back to us with new eyes.
Travelling at 50 times the speed of a bullet, Giotto's shield smashes into its first grains of dust. It's now 290,000 kilometers from the nucleus. And already, Halley's nucleus is clearly visible as a black dot. The sun's rays evaporate its ices into gas that carries dust in great jets, initially towards the sun. But then the fine particles are swept back into a tail, which extends far beyond the Halley camera's picture. Some chemical detectors on Giotto analyze the dust. Others register water as the main source of Halley's atmosphere. They also find carbon monoxide, but there's less of that further in. It appears to be produced by the breakdown of larger molecules. Halley is surprisingly rich in complex carbon compounds. Inside the dusty haze, we can see both shape and size. It's about 7 kilometers wide and 15 from top to bottom. There are small mountains, a chain of hills, and bright active regions that produce the jets. As Giotto closes in, some dust grains are now much larger. They punch holes in the outer layer of its shield. All the way in, other instruments on Giotto have sensed interactions between materials pouring out from Halley's nucleus and the solar wind, particles riding out on the sun's magnetic field. Electrically charged particles distort and intensify the magnetic field from the sun. We've burst through into a region that is pure comet. The magnetic field around us has completely disappeared. Here there's only the dust and gases that are lifting off the nucleus. On that, the darker regions are now believed to be a crust over more ices that have yet to evaporate. Already, the European Space Agency has won the best pictures of Halley's nucleus that anyone is likely to see until it returns after 75 years. And even then, only if we penetrate even closer inside its hazy cloud of dust. Giotto has been targeted to pass just 600 kilometers from the nucleus and does almost exactly that.
And we're about to show you what we couldn't show you before. Here comes the graphic, or we can't show the graphic. Okay, well, never mind. We're stuck with the same old graphic of where we see the comet and the probe closing in on each other at the moment. This is where Giotto is at the moment. It's right on target. It's beginning now to close in on Grigg-Skjellerup, which, of course, is its second comet. This is a first for the European Space Agency and for the world.
And we'll return to the Space Agency in Germany to continue our Horizon special.
30:49. We have very, very short distance to go. Johannes, I've been busy for the last few minutes, but have you heard of any data coming in? Before, actually, I noticed actually on my television set, I can see Gerhard Schwemm, who is the scientist in charge of operations today. Gerhard, how's it going?
Yeah, it's going very well, and you see it's getting really exciting now, just this half an hour before the closest approach. I have already left my chair to see the exciting data, and I moved to Fritz Neubauer with the magnetometer experiment, and he will explain you what he has seen.
Over to you, Johannes.
Fritz?
Yes?
I understand you have a lot of waves. Maybe you show us how they look on your paper.
Yes, we have some very interesting waves here.
Oh, we can see them
very
very
well.
well.
Developed, clear and periodic waves. And you can best appreciate them by comparing them with the data he acquired solar wind, which essentially shows nothing or very small
It's
activity.
a spectacular difference, yeah.
Here you have really these strongly nonlinear already, with also superimposed high-frequency waves, which are probably due to some complicated interactions.
But when you say high frequency, they're still very long wavelengths.
Yes, there again is several thousand kilometer wavelengths, and
they are produced by the picking up of water into the solar wind stream.
Yes, they are produced by the ions, produced by ionization of cometary material, and the free energy of these particles is then going into the generation of these waves, like in some, let's say, traveling wave tubes or so. In electric engineering.
Right, that's fantastic. Fritz, thank you very much. Can we come back to your waves later on? I did hear in my headphone, I don't know if anyone can confirm it, that was just, it wasn't, you're not actually catching dust. Okay, that would have been very exciting.
Yes, but we should talk now to Henri Rem. I think he has good news.
Yes, as you can see on the screen, we obtain with the electrons very clear waves with a period of about 1 minute. And these waves are really very well correlated with the magnetic field variations.
Well, that's fantastic. I think that's better than you had expected at this time, huh?
Yeah, we expected to have some waves between 50,000 and 30,000 kilometers.
So this comet produced a lot of waves.
A lot, much many waves than in the Halley Comet.
That's amazing. Can we actually go back to Halley's Comet for the moment? Because I find it remarkable that so many of the instruments are still working. In fact, for what some people thought was a kamikaze mission to Halley's Comet 6 years ago, we do seem to have virtually everything still up and running. And what happened to Giotto during those 6 years, and how the European Space Agency's engineers and scientists got it here, is a remarkable story in its own right. Let's pick it up at the point where Giotto was hit by something like this.
But as it turned out, on some of the scientific instruments, data was lost for only 20 seconds. And more was obtained as the spacecraft flew out of Halley's Comet. A few hours later, when some were ready to turn it off, the spacecraft was unexpectedly given a reprieve.
We had an enormous amount of fuel left as a reserve, and this was allowed us to make full use of that to choose a target for the future.
It took half the original fuel load to correct its course to get back to Earth in 1990. But as its orbit would take it so much closer to the Sun, this would expose the delicate electronics to its heat. The top must be turned away. But this also loses telemetry back to Earth.
Once the high-gain antenna pointed itself away from the Earth on our instructions, and that's the last we saw of it until 5 years later.
In any case, there were no funds to control and monitor the spacecraft while ESA planned and costed any future mission. Nor had they any further means of checking its condition, or even how that last maneuver had ended. The final instruction had put it into hibernation. Giotto would return to Earth in 1990, exactly 5 years after launch, and 6 of its own orbits. If there were to be any future mission, it would have to be woken up and checked out several months before that. February the 19th, 1990. To send a signal to the low-gain antenna required a huge dish near Madrid, part of NASA's deep space network, and a powerful transmitter.
Attention 6-3 transmitter is going to radiate 100 kilowatts. Any objections, call 7116.
Giotto was over 100 million kilometers from Earth. At the speed of light, the signal would take nearly 6 minutes to reach it, and they must wait another 6 for it to return. But then came Giotto's faint response.
And that was wonderful. Everyone thought, well, we're there, but we were by no means there, because that just told us that the spacecraft was somewhere out there, where we thought it was. It was not yet ready to speak to us.
The next stage would be to see if it would accept commands, so it could be turned to make the high-gain antenna point back to Earth. In response to their commands, nothing. But each major system had a backup, so for 4 days they worked systematically through the failure modes. Help in diagnosis came from an unexpected quarter. Because of the damage, Giotto is not perfectly balanced on its axis. It wobbles a little. The tiny low-gain antenna on the tip, which was all they could use at this point, rotates in a small circle, and this makes the frequency of any signal broadcast from it wobble too.
This turned out to be an amazing piece of information. We could use this wobble in the spacecraft, which related to a change in the frequency in the downlink signal, to see whether or not the spacecraft had changed its spin rate or whether it was maneuvering or not.
We knew we had a spacecraft. The only thing what we didn't know at that time is, could we switch it on, could we turn it around such that the high-gain antenna would point towards Earth to allow full communication?
During the reactivation operations, it was a mixture of frustration and almost elation at every small success in the steps towards the final reactivation. So over a week, most people went through complete range of personal feelings about the mission.
Yes, our strategy had eventually almost exhausted every possibility for success. We had been unable to maneuver the spacecraft, unable to activate the D-spin, which is the device which keeps the high-gain antenna pointing in the same direction even though the spacecraft is spinning underneath it. The next leg of the strategy said, okay, we'll make a total reconfiguration on board the spacecraft and select another power supply unit and then do the whole thing again, which is what we did.
Again, the Deep Space Network dish near Madrid sent the signal. The reply, when at last it came, went first to NASA JPL in California.
We predicted a change in a ripple on the signal, which we were expecting, a change in the period of that signal. And JPL produced a fax of this signal and sent it to us. And there was some delay whilst actually somebody at JPL had to join up dots on this fax to produce a continuous curve, which we could then analyze as soon as the fax arrived here. And it showed exactly what we had hoped to see.
They now had control of the spacecraft, but were in for their next surprise as they checked its condition. A mass of red on the screens. Giotto was far hotter than expected, which may have been why 1 hour later another unit failed and also had to be switched over to its spare. At the top of the spacecraft, heat from the sun was reaching vital communications equipment. To protect that, commands had to be sent turning the top away from the sun, which meant they had to delay checkout of the scientific instruments until Giotto was further out on its orbit and getting much closer to Earth.
I don't know if you remember from last time, we had pages and pages of red. Now we're back to very, very few red, which means that's the temperatures have now cooled down.
May 1990. Several instruments have now been checked out, and here it's the camera team, housed for the purpose in portable cabins. The camera is the most complex single instrument aboard the spacecraft and potentially the most rewarding. If they can get a picture, ESA's decision to continue will be much easier. One problem is sorting out any real damage to the camera from faulty reporting or commands that are not acted upon.
The mirror command has not been executed properly.
But at least the camera has been made to turn so that it can, in principle, find a target.
What to do next?
One maneuver does produce a clear result. When they turn the camera backwards to shadow part of the solar panel, that should result in a tiny drop in power. But there's no drop in power, so the baffle must have broken off. That's not vital, but there must be other damage too, because although the camera itself is still producing a signal, there is no clear image. This should be Jupiter.
There's cover mode again. This is on the nominal position, the nominal separation angle.
Final diagnosis, the aperture is blocked in some way.
Well, we're 16,872 kilometers from the comet, and there's 20 minutes to go. And we've just picked up news from the scientists that Chantal Levezé-Rigaud over there has picked up some interesting details with her OPE experiment. Johannes, over to you.
Did you really detect some dust already, Chantal?
Well, in fact, not yet dust, but already gas. For 10 minutes, we have already been flying inside the gas coma, and we see it very well from the CO+ data. So that's
CO+,
quite exciting.
huh?
We are within
Yeah.
the comet.
So there's carbon monoxide there.
Yeah, still quite
Very interesting.
Chantal, do you reckon you're inside the bow shock?
Well, no, we can't
Not
from
yet.
the preliminary data we have, but we'll find something later. But obviously, we have the data to find it.
Right, okay. Let's go and talk to Tony and see if he's picking up anything at the moment, just to see if I can confirm the rumour in my headphones about, 20 minutes ago that there was dust. I still don't know. It was about bow shocks instead, okay. And I wonder if Alan Johnston is picking up anything at all with his pickup irons. It is, fine, we have Alan Johnston now. You meant Alan rather than Tony, didn't you? Yes, absolutely. Alan.
Yes, well, the news is we're just crossing the bow shock at a distance of about 15 to 18,000 kilometers from the nucleus, and it's a much cleaner and much more well-defined bow shock than we ever expected to find here. So if I show on the plot here, you can see that the density is suddenly shooting way up, and the velocity is now starting to go right down. And if we look on the other displays on the next one, we can see that the distributions have broadened right out, so that they've got a lot hotter, and that is a very good sign that there is a proper shock wave there. So we're finding this particular piece of transition here is one of the most interesting that we've ever seen, I think.
Very good. And it's further out than was anticipated, huh?
Yes, it's about 3 times further out than we had expected from this morning's measurements.
Does that mean there's more gas? Or?
Well, there does seem to be more gas here, yes. The gas that we're seeing here now is much more dense than we would have expected on this morning's measurements. But one of the reasons for that could be that the comet has brightened up in the last few days.
Alan, can we come back to you later on that? Because it is thrilling. It's just that I have to say that after Giotto came out of hibernation 2 years ago, the combination like yours of instruments for studying the plasma was a major factor in the decision to carry on with the mission. And in fact, scientists whose instruments no longer worked were actually amongst those who wanted it to go on. In fact, it would be much cheaper than a mission for which a spacecraft had to be built and tested and launched. And in the end, the European Space Agency didn't have to go through the diplomatic nightmare of trying to collect new money from all the member states. As Giotto headed serenely towards the Earth, they had the decision, the funding, and the target. What they needed next was a sharp change of direction to reach it. This would be another first for Giotto.
For their course change, they planned to fly so close to the Earth that its gravitational attraction would swing it into a completely different orbit, farther out from the Sun.
If we had made this same correction using fuel alone, we would have needed 50 times as much fuel as Giotto was then carrying.
July the 2nd, 1990, 5 years to the day after launch, and 23,000 kilometers over Australia.
And in Australia at the time, it was night, and we were hoping that astronomers would be able to see a pinpoint of light. We were also hoping that it would be picked up by radar, but in the end, nobody saw Giotto flying past the Earth. No reports. No reports, only negative ones.
The next stage of Giotto's journey required a much improved diagnosis of the damage to its thermal insulation. It was clear that on its new orbit, further from the Sun, Giotto would get very cold. Could it survive this new peril? Its batteries had been designed to last only through the Halley mission, and the only source of power on the spacecraft is the solar panels. These had survived Halley. But now, much further out, they would no longer provide enough power for continuous operation. So, once again, Giotto was put into hibernation. This time, there was no choice. Meanwhile, its intended target, comet Grigg-Skjellerup, was also out of sight, on its way back from somewhere near the orbit of Jupiter. It approaches the Earth's orbit every 5 years, and last time, in 1987, from Colla Alto in southern Spain, their big telescope took a picture of it when it was near its closest to the Sun.
Oh, that's a picture of the comet showing an extended coma of about 150,000 kilometers diameter. It doesn't develop a tail, but this seems quite interesting for this extended Giotto mission to have 2 different comets. First, the Halley, very prominent, very bright, and now this faint object. Hopefully, one can learn more about the inner part of the coma of a comet which has less activity than Halley.
Because even then Grigg-Skjellerup was on the list of Giotto's potential future targets, the telescope tracked it across the sky so its orbit could be checked before it disappeared. In August 1991, they searched for it again by pointing the telescope and slowly moving it along the calculated path as they built up an exposure. It's quite difficult to spot.
Here, right here, you can see the comet. This tiny dot, a very faint image still at the moment of the recovery.
but easier to see on the printout. On a time exposure, the surrounding stars trail across the picture. Right in the middle is the comet, exactly where it should be. From now on, the orbit of the comet would be checked and recalculated time and time again.
Well, we can do better than that, because with us here, we actually have the latest photograph of the comet. Can you show us, Johannes?
Yes, this is a photograph of Grigg-Skjellerup, was really taken this morning.
Right.
At the Chile Observatory of ESO, and there's Klaus Jockers from the Max Planck Institute at Lindau, and he kindly somehow transmitted it to us.
Well, that's marvellous news. And in fact, as Alan Johnston was saying, it appears to be a little bit brighter than it was.
And of course, it's very valuable to compare the optical picture with the data we are getting.
Yes, indeed. Well, that's a marvellous picture, even though it's, in astronomical terms, 14th magnitude, which is a very, very faint magnitude indeed. Let's go back to problems with Giotto. There aren't any problems with Giotto. In fact, as I can see from the wall, it's only about 10,000 kilometres now from the comet, and it's closing fast. And so it's doing a really excellent job. Now we can see the reason for the main hazard, though still faced today by Giotto. It's what's called its orientation. Although it's still a long way out from the sun, and so to get power, the solar cell's angled flat onto it, and the high-gain antenna has to point back towards the Earth, which means it has to go into the second comet at a very, very awkward angle. Let me show you what I mean by moving across to the model of Giotto over here. And I must say that if we actually were at the real Giotto, this, of course, as you know, is the model, I bet it wouldn't look anything like as glorious and pristine like this. It would look like a car that had actually gone in, a second-hand car that had gone into a crash, covered in dust and stuff. As you know, in the first case of Giotto, it was designed to fly into Halley's comet, bumper shield first, and even then it was damaged. This time, the comet is actually flying in like this. So the instruments and solar cells are no longer protected as they were in 1986. In fact, if it goes in like this, the dust is actually going to hit them straight on, and it will get in here to the second layer of the bumper shield. So this is where Giotto is now, closing in very, very fast. And if you were actually inside the comet, looking out towards Giotto, this is the angle you'd see. There it is just here. Dust goes straight in from that side. And that's exactly what we'll see as it happens for real. And there it is. And I can see Tony over in the scientist headquarters. Tony, are you picking up any dust yet?
No, we just checked the screen. All zeros there, no dust yet, which I think is good news, although it's too early to say we'll be safe.
Well, what I find absolutely fascinating is that you were one of the first guys to pick up data from Halley. And today it's the plasma experiments, if you like, the ones that the public would find less glamorous, which are actually picking up all the exciting data. What do you think of that, Johannes?
Well, it's a different comet.
Yes. That's absolutely true. OK, Tony, we'll come back to you because we have 10 minutes, apparently, to closest approach. And you haven't revised. Obviously, you're still thinking 4 minutes to your dust particles, are you?
It's still fitting within our modelling predictions, yes.
Jolly good. OK, you stay within your modelling predictions. Johannes, what do you think of this comet? What sort of beast is it turning out to be?
Well, it's certainly too early to say, particularly since we don't know how close we are getting, you know. But what is surprising, of course, is that the intensity of the waves and the density of the ions, of the cometary ions, which so far have been mainly fragments of water, they are higher than was expected.
Is this because it's interacting more with the solar wind, or is it that the sun is more active?
Yes, we have to recheck the solar wind, but we have fairly good solar wind data before. If we get them afterwards, we can guess what the solar wind is now, because we don't know the clean solar wind now.
Right. Well,
but apparently there's more gas coming out.
Well, talking of the solar wind, Fritz is there waiting to speak to you. He seems to have some new data.
Yes, we have some interesting new data. We have now entered what is called the pile-up region, with no clear evidence for an abrupt change towards a shock or so. So we are now at fairly high magnetic fields, much above the solar wind. And this field, of course, is produced by the accumulation of magnetic flux tubes in front of the comet.
What do you think of that then, Johannes?
Pile-up region, that is to say, you see an increase in magnetic field intensity. Huh?
Yes, it's very high up.
How high are you now?
We are now at about 32, 35 nanoteslas. It's about a factor 2 to 3 above the field outside.
Yeah.
And what does that, how does that compare with the magnetic field of the Earth there? It's obviously quite a lot lower.
Yes.
Pardon, I didn't understand.
Oh, don't worry.
It's much lower.
Yes, it's much lower. Yeah. So we're picking up waves. We're now right inside the comet. If we're actually in the pile-up region, would you like to demonstrate to us, I think, on this model of the comet over here, if we come across here, let's remind viewers back at home who don't perhaps know as much about comets as our distinguished audience here, just where Giotto has now got to. Johannes, what's your best bet?
It's somewhere at the bow shock. I think we'll get more definite data about that. Now, the pile-up region, of course, is further inside because this red volume here, we call that a cavity, that's a clean cometary gas. And the solar wind cannot get into that, so the ions, solar wind ions, and the magnetic fields pile up in front of it, you know, and that's what Fritz is seeing.
And this, in fact, this yellow here actually indicates the magnetic fields inside the comet, and that's the true interior of the comet where you don't have any magnetic fields.
They pile up, and at the same time you get bent, and that's, of course, very important to understand the processes which go on to measure the details. This is just a prediction.
Well, I think it's truly remarkable that we're getting such good data back from a space probe that's battered and crippled and has really gone through it. It's amazing stuff. And as I come back, I can see Alan on the screen. Perhaps, Johannes, you'd like to talk to Alan and see what his latest data are.
Yes, Alan. So you mentioned the shock is very sharp, and that you can confirm? Or?
Yes, we can. It's developing even more now, and if we look at the distributions here on the screen, we can see that they're spreading out very widely.
Yes.
And so the temperature of these distributions is increasing very rapidly. And it all happened at about 1510. And that would be roughly about 18,000 kilometers from the nucleus. So it seems to me it's a much more well-defined shock than we'd expected. There's some very interesting data from the combination of instruments on the spacecraft, and it's much more different from Halley than we expected.
Is this going to make your life any easier in saying what is a typical comet?
No, but we're not looking for an easy life that way. It's certainly going to be very interesting to analyze the data, and I think we'll be able to do some excellent work on it.
That's great. Now, is there anybody else in the science room who'd like to come and talk to us and tell us what they're up to at the moment? Because there are 6 minutes and 10 seconds to closest approach, 5,000 kilometers to go, and closing quickly. There we go. Why don't you... The lady, by the way, that you can see at the moment, who's trailing a microphone and desperately trying to get hold of scientists, actually used to be a champion sprint runner for her county back in England. She's very good at persuading people.
Here's Henri Rem.
Yes, as you can see again on the screen, we have fantastically large waves, and beginning at around 1510, and we think this is the beginning of the very large shock. So the beginning of the shock is about 17,000 kilometers from the comet.
And so that agrees with the ion data, huh?
It's electron data.
Yeah, but I mean ion data show the same distance.
Okay.
Yeah.
Before, we have an increase in the electron fluxes, and we see this is a foreshock.
Can I just interrupt for a second? I'd like, Johannes, if you could just talk us through exactly what we're seeing on the screen for the viewers back at home.
Yes. In the top one, you see the density of electrons. Electrons are the smallest members of the plasma, very evasive, and Henri has the only experiment which can detect these electrons.
Right.
And he just explained it's rising with time. And the lower panels show very intense waves, and that's at the point of the shock waves, and that's exactly at the point where Alan, with his ion instrument, sees also the shock waves.
They've all confirmed each other's results in a way.
Excellent.
I wonder how Susan McKenna-Lawler's getting on, or is she too busy to talk to us at the moment? Susan, would you... Chantal, Chantal, hello. How are you getting on?
Well, nicely. We have been observing the dust since quite a few kilometers or minutes. I don't know what it is anymore, but
4 minutes to
we
go,
were in the
Chantal.
dust clouds at about 20,000 kilometers from the nucleus.
And what do you see exactly now?
Well, now we see a significant increase in the dust signals, and as you know, we try to find the missed distance from the shape of the curve.
Chantal, what I don't understand is if you're detecting some dust, why isn't Tony McDonald getting anything on the dids?
Well, I think we don't see the same level in size of the dust grains. The ones we observe are certainly
You
much
see
smaller.
the small grains mainly because you have an optical experiment,
Yes,
and he sees the impact. Huh?
Yes, and he's going in at the wrong angle as well, isn't he? He's going in at a slanted angle. Well, it's now 3 minutes and 15 seconds to closest approach, 2,700 kilometers to go. It's like one of those planes you travel on where it keeps on telling you where you are and when you're going to reach your destination, except here, remember, we're out in space and we're 214 million kilometers from planet Earth. It's very exciting news indeed. We, I gather, are going over to Susan McKenna-Lawler to see what Epona has picked up. There she's gesticulating. She's gesticulating even before she has her headphones on, so she's obviously finding some interesting data there. I know that the red trace that she detected yesterday was much higher than she was expecting for the number of active particles around the comet. Can she hear us at all?
Hello, Heather. Yes,
Hello
I
there,
can.
Susan. How are you getting on?
Well, I'm rather surprised by what I see here. I have traced, we're plotting omnidirectional counts in channel 1 of our telescope 1, and we're seeing rather dramatic fluctuations there. We have a rise in counts close to the bow shock, and then an oscillating behavior. And I don't know what it means at the moment. We're just recording it.
Do you think you're in what is called the mystery region that was detected at Halley's Comet, where people just couldn't explain what was going on?
Well, there's a mystery region that is rather far out that Henri Rem talks about.
Yes.
There's also the great burst of particles that Epona detected in the cavity near Halley's Comet, but I'm not at all claiming that what I see now has anything to do with that.
We'll let you get back to work, Susan.
All right,
You're obviously doing a grand job in there.
All right.
Yes. We're going across to Tony McDonald now, who I hope has picked up some dust. If he hasn't, I guess the sweepstake is off, so if you put your bets on it, never mind. Here we are, Tony. Hello, Tony. It's Heather here. Have you picked up any dust yet?
No dust events yet, and it's -2 minutes, so...
It is indeed. It's -1 minute, actually, 1 minute 15 seconds at the moment. Okay. Do you find that very strange, or do you think the particles are much smaller than in the case of Halley's Comet?
Well, we don't really know whether the comet is really turned on or not, really active with regard to dust, although it's been visually much brighter.
Yes, so presumably a comet can give out a great deal of gas, but it has to be rather churned up to start, as it were, getting its surface ablating as well.
Yes, indeed. On Halley, you see, we found that there was a tremendous number of large particles. Now, we are hearing from the optical experiments that there may be some small particles scattering the light,
Yes,
but no
we've heard
big
that from
ones yet.
Chantal. OK, well, thank you very much for talking to us. We have 40... Yes, we have a very, very short time now to encounter, as you can see from the countdown on the big screen just there. I hope we don't have the same situation as we had at Halley's Comet, when the screen wobbled and went blank. In this case, I don't think we're going to. And what is your feeling about it, Johannes?
Well, in a way, if they're not big dust counts, the chances are pretty good, I guess. But of course, there always can be a single one, you know.
What about gas jets? Could that be a problem coming from the solid nucleus?
Not the gas, but the gas jets take dust along.
Yes.
And the dust is the dangerous thing, you know.
Well, here we... 4, 2, 1, 0. Tony, we're at the comet. We've passed it. Where's your dust?
It's a clean comet.
It's a clean... Well, I'm delighted to hear. Obviously, it's a green, environmentally friendly comet that isn't chucking dust all over the universe. So maybe we ought to... Let me go over, if I can, to the flight dynamics people, the engineering...
An event!
Yeah, well, an event!
Yes.
Yes.
We have a dust index.
We had one event. Would you, Tony, Tony, can you still hear me?
Yes, indeed. We can publish a flux curve now rather than really very significant.
I would like to suggest that it's probably small number statistics and no one would actually believe you. Presumably, you couldn't even estimate at the moment just how big this event was.
Oh, we could do a lot of statistics. No, second event.
Great.
Oh, good. Second event.
Why are you picking up dust when you're actually
Absolutely.
beyond the nucleus? Does
Yes.
this...
Well, the predictions did actually say that if we're going to look for big ones, there would be big more after the encounter rather than before.
It's okay.
But of course, we do have that uncertainty of encounter time. We don't know that yet, really.
Yes. Right, let me backtrack again to all of you viewers who are watching at home and wonder what on earth an event is. I do agree, we haven't explained what we mean. What we mean is that Giotto has been hit by, I think at the moment, is it 2 or 3 particles? That might not sound very exciting, but for a completely dust-free comet, for the Giotto probe to collide with bits, it's very exciting news. It means that as well as all the waves and gas we found pouring off, there really is a solid comet in there with a solid nucleus from which bits of dust are boiling off. And can I come back to control room? How many dust events have we had so far?
It's either 2 or 3.
It's
We're
either
not sure
two-
yet, because they may have been too close together.
It's 4 on the display.
In fact, there's a count of 4 possibly. We have to confirm those yet, though.
Fine. Johannes, how do you feel about this?
Yes, it's amazing, but as Tony was saying, we seem to have, there must be some dust,
Yes.
very fine dust, and rather few bigger particles which he detects.
Yes.
So the grain size distribution, as we call it, the relation between small and big dust may be different from that in Halley.
Is that because Grigg-Skjellerup is a much older comet that's tramped around the solar system many more times than Halley has?
I think this is one of the things we have to find out. If older comets, I think in this respect, what grain size concerns, there are probably many different comets, you know.
Well,
but it could be connected to that, yes.
Well, we've had 4 events so far, and those events actually came post-encounter rather than pre-encounter. Now, is that because Giotto is going into the comet at a different angle from when it was going, as it were, sort of end-on to Halley? What do you think the reason for that is?
Yes, first of all, of course, we don't know the moment of closest distance better than a minute, so maybe it was a little delayed. That would be very interesting if we can find that out. And then, of course, this is statistics. And finally, the emission of dust is not uniform.
Could it well, as you say, it could well be that we actually passed closest approach a minute later when Tony got the maximum of his
Of course, with 4 counts, I wouldn't say that. If he would have 400 counts, he would immediately be able to say that.
Don't tell that to Tony McDonnell. That's what I can say. I would like to go across to flight dynamics if I could. Yes, I'd like to talk to Howard Nye. He's sitting there waiting. Howard Nye, can you hear me?
I can, Heather, yes.
Yes, are you okay? You're okay to talk to me at the moment?
I can say something quickly, yes.
You can say something quickly. What do you think about Tony's dust events? Does that prove that maybe closest approach was a minute later than we thought?
That's perhaps the case because we only observed on the ground here some effect on the spacecraft. We're seeing the spacecraft wobbling a little bit.
You are?
We are, yes, and the spin rate has increased by 0.01 of an RPM. The predictions that were made before the encounter said that the spacecraft could speed up during this encounter, and it did very, very slightly.
Right. And what sort of angle is it wobbling by? It's not causing serious problems for communication, is it?
It's very, very small. In fact, if you look at the display over here, you can see the wobble.
Oh, yes, I'd like to see the
here.
display, please, if you could bring it up for us.
The wobble is very, very
on the pink
slight here.
Oh,
it's
very
very,
tiny.
very small compared with what we saw in 1986.
Right. Well, thank you very much indeed. I hope we get back to normal, but it doesn't look like a serious problem at all.
Absolutely.
I gather we're now going to Fritz, if you'd like
Yes,
to speak
yes.
to him.
Fritz, can you hear us?
Yes, I hear you. Did they notice that?
Fritz Neubauer?
Oh, they picked it up on that.
He's staring at his waves so avidly. I don't
Yeah,
think he's heard
he's
you,
absorbed
Johannes.
by his waves.
Johannes wants to speak to you, Fritz.
Pardon?
Ah, pardon. Fritz, can you hear us over in the studio?
Yes, but not very well, I must say.
Okay.
Maybe why don't you just explain what you are seeing now? Can
We are now seeing a retreat from the comet. We are on the outbound path, and during the encounter, we have apparently not passed through the cavity because the magnetic field stayed up fairly high, so we must have passed really at a longer distance, a distance more than 100 kilometers from the comet.
And how high was the highest pile-up field strength?
The highest field was about 70 nanoteslas.
And you would expect something like 80 to 100 at the maximum? Or?
Well, we had expected a little bit lower, but the field a little bit lower, but the interplanetary field was particularly high in this case, so it's about the ratio expected.
And does that mean we were rather close to the cavity, huh?
Yes, we must be fairly close, but we haven't really gone into it.
Right, you haven't gone into how close you might have been.
The structure is relatively complicated compared, for example, with Comet Halley. The structure is fairly complicated, so we may have some other things in the data.
Fine. Thank you very much indeed, Fritz. In fact, we've moved across now to flight dynamics, where I can see Trevor Morley being wired up for sound over there. Trevor, I understand that the drop-in count rates with the DIDS experiment might not have been due to the fact there wasn't a lot of dust around, but that your link with the Deep Space Network with NASA was faulty. Is that true?
No. What we are seeing is that immediately after Tony reported his dust impacts, that the spacecraft started to wobble very slightly.
Right.
And also we saw a very small change in the spin rate. And both those things that we are seeing are consistent with being struck by dust.
Right, so in fact, I'm sorry I mean, the DSN is wonderful, so I will not knock it at all. How close do you personally think you got to the nucleus? Have you got any hunches about that?
My hunch would be within 300 kilometers, but I wouldn't like to bet a lot of money on that. And hopefully we will find out later on after all this data has been examined.
No, we won't. We'll find out in real time this afternoon if anyone's going to push anything through their pocket computer.
We could ask Chantal.
That is a good idea. And in fact, if we pass 300 kilometers, we actually have then passed closer to this comet than we actually succeeded in flying towards Halley. I think that's incredible for a space probe which is blind, disabled and crippled and can only see, hear and smell. Now we're back, I gather, back into the scientists. There is indeed a pocket computer. I don't know what they're doing with it. Maybe they're calculating the distance as I asked them to. Johannes.
Well, the only thing we can say right now is that we were quite close to the nucleus. It just seems to me we were closer than 200 kilometers from the nucleus.
So you keep calculating and tell us more exactly later?
Estimating it just right now, but it was quite close.
Yes, very good.
Well, that's pretty amazing stuff, isn't it? To fly, I mean, it's a triumph of engineering, and it's a triumph to actually get the scientific data back, because we've heard how complicated that is. First of all, orientating the spacecraft, and then getting the experiments working again. I also feel, what I find amazing about this whole mission is that the spacecraft was switched off and in hibernation for 5 years. No one was talking to it. If I was told to go into hibernation for 5 years and no one talked to me, I'd feel pretty put out.
Yes.
Is this a way of cheapening space missions? Is this a way of possibly not keeping contact with the probe all the time?
Well, I think it's a very interesting experiment in this respect, that if you have nothing to measure or nothing particular to measure on your way, of course, it's a cheaper way. And the reawakening of Giotto is, as you mentioned earlier, a very particular feat. And I guess that other space agencies and other engineers will look very closely and say, maybe one of these days we can use this technique and save money and power, you know.
I hope so. Let us set some of these ideas in context. What I'm going to do now is to wander over to the Giotto model and show you some of the experiments which have really performed so brilliantly this afternoon. And we're very, very proud of Giotto. Just to remind you, although I'm sure that many of you in the audience don't need reminding of as to what Giotto looks like, we have the camera, which of course, unfortunately, does not appear to be working at the moment. And it comes by painfully slowly, but I will, while we're standing here and waiting for various other experiments to come around, up on the boom, which holds the big high-gain antenna that you see, the sort of bucket shape there, we have right by my hands the Fritz Neubauer's magnetometer experiments, which have picked up such amazing stuff this afternoon from this comet, have detected these enormous waves of 1,000 kilometers out in space. This is part, I believe, of the Johnson plasma analyzer sitting in there, tucked in behind there. And here we have the experiment of Joachim, which is not working on this approach simply because, as you can see, the tube is not at the correct angle for hitting the comet and the dust to go up the tube, as it were. And as we carry on, I think this is probably going to take too long to show you all the experiments. If this was the real Giotto, it would make my life an awful lot easier, because Giotto actually goes around 4 times a second. This Giotto processes in a rather gradual way. Well, at this point, I want to introduce one of the youngest guests today. I'm going down to find him over there. If you recall, back in the old days, back in the 1986 encounter with Halley's Comet, and I'll follow down here. Back in the 1986 days of the Giotto encounter, we had a terrible problem of knowing what had happened when the pictures suddenly stopped coming. And those of you who saw the programme back in 1986 will remember that there was one young man in the audience who looked at the pictures and he said very clearly to the presenter, "Mister, I think it's busted," which, for those of you for whom English is not your first language, means, "Mister, I think Giotto has been hit by something." And all the scientists who were watching in Greenwich pooh-poohed him and said, "Oh, no, of course it hasn't." But he was right. And I'm delighted to introduce Lee Sproats.
Hi.
How do you feel about today?
Very interesting results indeed.
And now let me fill in a bit of background. Lee, you have now become an astronomer yourself, a professional astronomer.
Well, not yet.
Not
got my
yet.
degree.
You got your degree.
There.
And what sort of degree did you get?
Astronomy.
And where was that from?
At University College London.
That's tremendous. And where are you going after you've got your degree? So you're going on now to do your PhD. I understand, ladies and gentlemen, that Lee actually just failed to get a first-class honours degree by 2 marks.
Just about.
Never mind, I only got an upper second as well. Where are you going to do your research?
Hopefully in Mullard Space Science Laboratories in Holmby St Mary to do cataclysmic variables.
Cataclysmic variables?
Yep.
Well, it's a long way from comets, but you will be a near neighbour of Alan Johnston, of course, who works at MSSL as well.
Just about, indeed.
Tremendous. Congratulations, Lee.
Thank you.
It's nice to see you at the second encounter of Giotto with another comet, maybe a third time.
Possibly.
Okay. Thanks a lot. Well, wandering through again. And I'm going to go back to Johannes Geis now to find out if we've got any updates on what's been going on, to see if, thank you very much, to see if Tony has got any more particles. Johannes, what's the latest? Do we have any more news?
Yeah, all the experiments want to talk. Maybe we talk first to 1 or 2 of them, which we have not talked to. There's the radio science experiment.
Yes.
Let's see if they see a shift in velocity of Giotto, you know. Last time was a very small shift, and we would, of course, expect it's even smaller this time.
Yes.
But let's see if they really can detect this shift.
Right. I understand that Martin Penfold is actually waiting there. Yes, I can see him on the video screen.
Yes.
Johannes, would you like to ask him?
Yes. Have you seen what is technically called the Doppler effect? In other words, some small shift, or have you seen the wobble?
What I can say now, what my colleagues told me from JPL is that we detected a Doppler shift coinciding with the time with the first dust impact, and we have a slight notation.
Yes.
That's what I can tell you now.
So that must have been a big impact, no? The first one.
It might be a very big impact, yeah.
Well, that's...
Thank you. Yeah.
It's exciting to think that a comet which has got such low activity can actually produce this kind of effect, and also maybe it tells us we really have gone quite deep into the nucleus, or quite deep into the coma of the comet. Have you heard if anybody's picked up the mystery region, which we heard so much about at Halley's Comet, the region where there's no pressure, nothing much going on?
I would guess, but we can ask them, this mystery region, of course, is turned up as Halley, and it may be different in every comet, and it's because it's mystery region, may be difficult to identify so fast,
Certainly.
you know.
I think at this point of the programme we ought to address ourselves to the problem of what's going to happen to Giotto after this encounter, and maybe after we've talked to Tony McDonnell we can go on to that.
Yes.
Tony, I see you've been wired for sound. Do you have anything to report?
Well, yes, the 4 particles we did detect were very large ones.
Yes.
So there's a lot of mass about, but it does seem to be in the big ones.
Right. What sort of mass would you estimate, first off?
Well, we're talking about probably 0.5 millimeter for the very biggest one, which might have hit the whole of the spacecraft. Perhaps a little bit smaller than the ones actually hitting our sensors, but quite a big particle, perhaps.
Thank you very much, Tony. I can see that Howard Nye is available in mission control. Howard, I think it is safe to say we have definitely passed comic Grigg-Skjellerup now. We're out of the woods. And can I ask you, what are the plans to, what are you going to do with Giotto now?
Well, we have a plan which we use on Monday, which is to do a large orbit correction maneuver to take it onto another flyby past the Earth in 1999.
Can't you put the space probe down? Poor little thing.
Well, it seems to be indestructible. It's been past 2 comets, and I think the comets are probably coming off worse for wear than the spacecraft.
I think that's absolutely wonderful news. Do you have enough fuel left for this manoeuvre?
We have certainly enough fuel to do the orbit manoeuvre on Monday,
Yes.
and thereafter we'll have very little fuel afterwards. We have to see what we can do with it.
And what do you feel about after, when it comes back to the Earth in 1999 and makes a swing by? Are there any plans, informal plans, that you might be able to tell me about now?
Yes, we're looking at potential targets, other comets, which would be reachable with the minimum fuel and under the conditions that Giotto has to have in order to meet comets.
That's phenomenally ambitious. I really wish you the very best of luck with that plan. And wouldn't it be wonderful if, like in the 19th century, we had a really great comet coming by at the end of this century that would just put itself right on Giotto's path?
That's right.
Well, let's pray for that one. Thank you very much indeed. What would you think of a plan? It's an amazingly brave and audacious plan to send it to another comet.
It behaves very well, and at the same time there's some surprise, like this one big particle, you know, was as big, probably as the biggest hit by Halley, you know. I suggest we go back to the plasma and fields experiments and make another round, including Hans Balziger's experiment.
Yes, indeed. Well, in fact, what about the comet itself? What about Grigg-Skjellerup? It's an old comet. It's obviously losing matter as it goes around the sun, both gas and dust. How long would you estimate that Grigg-Skjellerup has to exist anymore?
I wouldn't know, but it's not a matter of hundreds of years. It's much longer. And but I wouldn't know how long. It will probably go less and less active, but today it was fairly active.
It was
in
very
terms of gas.
put on a good show for us. I can see that we have Alan Johnston and his... I can see a finger pointing at a screen, looking very excited. Alan Johnston, are you picking us up there?
Yes, I am.
And what are you finding?
Well, we're starting to see the structure on the outbound leg now, and as far as we can see, it's following the same sort of structure as we found on the inbound. It's too early yet to say whether there will be any strong asymmetries, but again, I think you can see, perhaps from this plot here, that goes through the point of closest approach, that there is a great deal going on. It's a very dynamic situation, and we see in the middle here that the speed of the iron slows way, way down and almost drops off the bottom there. And then it comes up again on the other side.
That was at closest approach. Huh?
That was the moment of closest approach, yes.
So would you say we were rather close to the cavity in this case?
I think we could well have been, but I don't think the data I've got here will be absolutely conclusive on that.
Yes. I understand that all of you are going off this weekend to a retreat where you're going to have a sort of first sort of stab at your data in some secret castle in Germany. Is that right?
Well, some people may be, but unfortunately I can't. I'm heading off for a conference in the US next week.
Oh, dear. Oh, some people have to suffer, Alan, but you've obviously got some good data, so I'm not sorry for you at all.
Yes, we've got some excellent data, and I think the fascinating thing is that it's so different from the data we got at Halley.
It's going to make life much more difficult for all you cometary scientists, though, isn't it?
It'll keep us in business for another few years.
I'm delighted to hear that. Well, what do you think? What sort of comet is this, Johannes? Generally, what do you think?
It seems to be full of gas and not so much dust, but fine dust. So maybe we should go back to Annie Chantal and see what she has.
Yes, is Annie Chantal there? Annie Chantal's experiment, of course, looks at the sort of the dust halo, looks at the glow of how...
Yes, it's an optical experiment, so she looks at the whole amount of gas which the light penetrates.
Annie's there. We go to her very quickly. Yeah. Annie, anything to report, but very briefly?
Well, we confirm that the mist distance was certainly smaller than 200, 250 kilometers, and that the closest approach took place a little after 1530 by 1531 and a few seconds.
Thank you very much, Chantal. Anyway, all we've seen and all that's been discovered today will, even though it's amazing, be only another modest step towards what we'd really like to know about comets. Sadly, one future mission to fly alongside a comet and watch and measure how it changes as it approaches the sun was cancelled by NASA earlier this year to save money. But we're still hoping for a future joint mission in which ESA joins once again with NASA that could be even more ambitious. It's called Rosetta.
ESA's Rosetta is designed to land on the nucleus of a comet and collect samples of the crust, minerals, organic materials and ices. It takes a core from beneath the spacecraft, collects some from the surface around it and seals them away in deep freeze for the journey home.
I can see Gerhard on the screen just there, and in fact Gerhard is actually wearing two hats today. There's a great celebration going on in the background there. What are you lot up to? Gerhard, as well as being the project scientist for Grigg-Skjellerup, you're also involved in Rosetta. Why do you want to go and snatch a bit from a comet?
Yeah, I think after we have experienced and really could celebrate this textbook encounter today, the second encounter of Grigg-Skjellerup, now we should go a step further and bring back material from a comet nucleus, that we could do a really detailed, in-depth chemical analysis of the most primitive matter in the solar system. And, you know, we had a lot of scientists here from all over the world, and I think we should take this opportunity really to promote a comet nucleus sample return mission that should be done by all the agencies together to bring this material into the laboratories where we could adjust our instruments to what we will get, and not that we have to develop the instruments 10 years in advance and then we'll get all the nice surprises. I think we really should go for an international collaboration on that and really go to this next step after these wonderful Giotto missions to the comets.
Absolutely, I could agree with you entirely. In fact, talking of international collaboration, I understand that in the audience we have the new administrator for NASA, who is sitting over there with the spotlight on him. Daniel Golden, I'm delighted to meet you, and congratulations on your new post. What do you think of the mission today, and do you want to go and ride on Rosetta?
I'd like to ride on a shuttle.
And so would I. I'll join you there. Thank you very much indeed.
You're welcome.
I also understand that in the audience we have Alek Galaev, who's the director of the Cosmic Research Institute in Moscow. I thought you were over there. You're hiding from me. Okay, fine. And I noticed that you are wearing a Halley's Comet tie.
Comet is unidentified, actually.
It's an unidentified comet. Now, talking of international collaboration, you, I understand, in Russia have a mission coming up next year?
Yes, we have solar terrestrial physics mission,
right.
Interball.
And you also have the Mars mission, I gather, where very many of the scientists from this mission have experiments on board to detect plasma.
Yes, that's true that in our Mars mission we cooperate with a lot of our colleagues from Europe.
That's it. Thank you very much, and good luck with your upcoming missions. It's a very exciting time for space. Well, today's encounter between Giotto and Grigg-Skjellerup has really cast fresh light on all the discoveries that brave little space probe made at Halley's Comet. We can see those findings in a new light. Now we have two comets to compare. You've heard all the scientists talking about that. But this is really just the beginning. There's so much work to be done, both for the scientists working on Giotto's findings and for those who will use the data to plan missions for the future. Johannes, as a scientist who's been involved in so many space missions, what's your verdict on today's exciting goings-on?
Well, first of all, it's obvious it was very successful. I think the Grigg-Skjellerup comet has behaved very well. Was few dust numbers, but still is exciting enough. We got some wobble and so on, so we had to tell something. What was really surprising is how good the data were concerning the dust and the plasma.
I couldn't believe that myself. I hadn't expected them to be so clean.
Yeah, so the experiments worked very well. And at the same time, we have 4 or 5 experiments. We haven't even talked to all of them.
Yes.
The ion mass spectrometer of Hans Balsiger, for instance, has also picked up the water ions.
Oh, now that's exciting, because we've spoken to Hans Balsiger, and I didn't realize he was picking those up.
So there's a lot of confirmation also. The electrons and the ions match and have to be matched. So it's a very great success. I think obviously it was worthwhile to investigate these 2 different comets. And I think, in closing, I would say it's a very good example of a European cooperation.
Indeed it is. And what a memorable event this has been to crown international space here. But it's just the beginning of several exciting projects which include trips to Mars and Jupiter, and even further afield to Saturn's bizarre moon Titan. But for me, the wonderful part of the day was the sheer buzz of a live space encounter and the amazing news that Giotto itself may be going on yet another adventure of its own. But for the moment, it's a temporary farewell to Giotto. We wish you a well-earned hibernation, and good luck to all the scientists here today who will be going away to work on their results. Now it's time for us all at the European Space Operations Centre in Germany to take our leave of you too. We hope you enjoyed the action as much as we have. From Darmstadt, bon voyage to Giotto, and goodbye.
Well, if you'd like an illustration